Hello students, welcome back. Let us resume our discussion in section 3. We went through the baby definitions of the GCD and LCM in the first video, and we proved that both the GCD and LCD exist uniquely based upon this baby definition. And then in the second video, we went through Bezout's definition of the greatest common divisor. Number 1, non-negative. Number 2, common divisor. And number 3, linear combination. 3 ingredients. Then it turns out such an integer exists and exists uniquely. We didn't prove the existence. We postponed it until the end of this section. Yes, we will do it just later. We did prove the uniqueness though, and along the way we used this. And also we proved it, as a matter of fact. Any common divisor divides this D. Remember all those? And then we use these to establish relatively prime or coprime. In that case, we don't need to consider all 3. We only need number 3. The red condition here, the linear combination, because 1 is special. 1 is whole number, of course, greater than or equal to 0, and then 1 divides everything, so green and blue are automatic. So we only need to check red. So whenever we have relative prime, forget about green and blue, just check red. And let's utilize some problems associated to those. After all, our aim is to learn to utilize this Bezout expression. And for those, we have 3 ingredients. And if you have to consider just one of them, the most important one here, then that's going to be the most basic exercises. So that's where we're going to begin. Alright, first example here. Let A and B be integers and the GCD is D. Show that the integers a of d and b over d are relatively prime. Basically, we have to prove this. Here, a over d and b over d may look like rational numbers, and they are rational numbers, of course, but d divides a and d divides b as well, so they're both integers. Yeah, every integer is a rational number, so calling those as rational numbers is not wrong, but you know what I mean. Even though they may have fraction form, they're not really true fractions, they are integers. So, how to prove that? Well, what you want to prove is this a over d and b over d satisfies this linear combination form, this red condition. And what do you know? We know this. So from here, we can say ax plus by is equal to 1. That much we know. And then, whoa, excuse me, that much we know. And from here, a over d times some integer, something, and then b over d times some integer, something. That's what you have to prove. Any idea how to do this? It's going to be trivial. All you have to do is to divide both left-hand side and right-hand by. Look, I'll stop there. There's a hint, but I'm not going to show you that. I want you to work out. Got it? Well, in case you didn't get, here's a hint. Actually, this is not a hint, it's a full proof. From here, divide both by d, then we have that, and x and y are both integers, so yeah, that's a full proof actually. Alright, okay, part A is done. How about the next problem? Prove that every non-zero rational number can be simplified to the lowest term. Oh, this is one of the rare problems that we have to deal with rational number, real fraction. Basically, that's what we have to prove. Given rational number a over b, and of course, if numerator is 0, then we get 0, so that's trivial case. So let's consider non-zero integers there. Then a over b can be reduced into p over q, where p and q are relatively prime, so cannot be reduced any further. Is there any way to simplify this a over b into something like that? Something simple? What do you think? Got it done? I hope everybody got it done. That's all there is. Divide each by GCD. If you do that, then what do you have? A over D and B over D are coprime, or relatively prime. And that's precisely what we wanted all along, P over Q. Here's a hint. And again, this is not a hint. This is full proof again. A over GCD, so that's D. So that's D. And then G over DCD, again, that's B over D. And then we prove that A over B and B over D, those are relatively prime in the previous problem. Yeah, in order to become a full proof, you have to mention that we did it in part A. Okay, so hint may be appropriate. Okay, getting warmer. How about the next problem? A divides C and B divides C. In other words, C is a common multiple, and A and B are relatively prime. Then A times B divides C. How's that? Any idea? Well, we will have to utilize that A and B are relatively prime one way or the other. So let's rewrite this into ax plus by equals to 1. Or if you don't like x and y, you can use some other characters like r and s or m and n, whatever. Let's start from here. And somehow, let's prove that C is divisible by A and B. What do you have to do? Got it? Got the idea? Stop the playback and try. Okay, time is up. Here's my hint. A times x times c plus b times y times c is equal to c. That should help. How will that help? Well, we got c, and then we want to prove c is divisible by a times b. So left-hand side will be a times b times some integer is c. That's our basic goal. So what do you get here? Any idea? I'll stop here. This notebook has more, but I'm not going to show you at this moment. Sweat it out first, try to get as much as possible, and then if you're really stuck, open up the hint and try to complete it on your own. I'm not going to do any further. Next. That's the hardest bunch, I think. Yeah. A was the easiest. This was a bit hard. This was still a bit harder. This one is gonna be, yeah, this is gonna be a real challenge. So, what do we have here? A divides B times C, and A and B are relatively prime. Then A divides C. So A and B have basically nothing in common. So entire A is a factor of C, how do you prove that? If you knew the prime factorization, maybe you can work like this. A is P1 times P2 times P3 times and so on as prime factorization. And B is Q1 times Q2 times Q3 times and so on, like this. And then they have nothing in common, they're all different. And A divides B times C, so C must include all the prime factors here and also all the prime factors there. Because there's nothing in common, there's no ambiguity, so this kind of argument will work. There's a problem though. Number one, we didn't study the prime factorization yet. That's number one. Number two, as a matter of fact, we need this lemma, which we call Euclid's lemma, to prove the prime factorization. So you see, you cannot use prime factorization to prove prime factorization. So that's no good. So do not think of it in terms of prime factorization. Try to utilize this Bezoos linear combination identity. You see, GCD of A and B is 1, so AX plus BY is equal to 1. Somehow try to utilize this. Well, what did he do last time? Last time, here, we multiply C to both left-hand side and right-hand side as before. And then somehow what we want to do is express this thing, manipulate this thing, so this is A times some integer. That's what we have to do. How are you going to do that? That's going to be your challenge. I guess I'll stop here. This is going to be a bit bigger challenge, but I'll stop here. And good luck completing this problem and the others too. Actually, the proof is here, some hint is here, but I'm not showing you that. Try to get it done without those hints. Hopefully, you can all get successfully complete.